My name is Terrie Simmons-Ehrhardt, and I will be presenting on open resources for virtual osteology. Many of us in anthropology are now working with virtual osteology or digital representations of skeletal anatomy, either generating or using 3D models from surface scans, photogrammetry, computer tomography, or microcomputer tomography for teaching or research. Virtual osteology workflows can now consist entirely of free or open source resources, including rendering and analysis software and web sharing of interactive 3D models and CT volumes. Data sources of virtual osteological data include online CT repositories such as the New Mexico Decedent Image Database, the Cancer Imaging Archive, MorphoSource, Embody3D, the NIH 3D Print Exchange, and many other biomedical sources can be found listed at the MedSeg site. 3D human osteological models can be found at MorphoSource, Embody3D, the NIH 3D Print Exchange, and Sketchfab. Most of these data sources are openly accessible with or without registration. In addition, the free software options for interacting with 3D models, as well as for rendering and analyzing biomedical imaging data, have increased the accessibility of virtual osteological data to anyone willing to learn. Free CT rendering and analysis options include 3D Slicer, the MedSeg web browser-based viewer, and Dragonfly, which is free for academic use. These programs support high-quality rendering and quantitative analyses that for anthropological applications may even exceed the features of commercially available software. Free programs for working with rendered 3D models include MeshLab, MeshMixer, and Blender. These programs allow for some quantitative analyses, the generation of visual products for dissemination, and preparation for 3D printing. The Cancer Imaging Archive contains de-identified medical imaging data of various modalities, with CT scans available for more than 8,000 subjects. Most collections on TCIA are accessible without registration and are made available under the Creative Commons Attribution 3.0 Unported license for commercial, scientific, and educational purposes. Individual datasets may have further use specifications and restrictions. Scans and DICOM metadata can be previewed within the browser before download. Medical datasets from TCIA can also be directly loaded into the free imaging software 3D Slicer via the TCIA browser extension, allowing for quick access to a source of de-identified modern human skeletal data. After using the TCIA website to identify collections and/or subjects of interest, collections and specific scans can be accessed and loaded into a 3D Slicer project or database. This video shows how quickly you can access TCIA data, perform and customize a volume rendering by adjusting the preset values, and clip the volume rendering to visualize specific areas of interest, such as the pubic symphysis. The ease of accessibility can minimize the learning curve for working with CT data and increase the possibility to generate large amounts of quantitative or non-metric trait reference data. 3D Slicer's large user and developer community has led to many advanced features that support high-quality volume rendering and segmentation of CT and microCT images and computational analyses of 3D models. With the volume rendering module of 3D Slicer, a 3D visualization of a CT or microCT data volume can be quickly viewed and customized. Interaction with the volume rendering includes custom rendering options by altering preset transfer functions and cropping of specific areas of interest, a collection of measurements and non-metric traits, simultaneous visualization of 2D orthogonal slices and the 3D volume rendering, and generation of animations for dissemination. The Slicer Morph extension has added tools to support microCT processing, including a direct link to MorphoSource. Interested users are encouraged to visit the Slicer discourse to keep up with updates and seek support. 3D Slicer's segment editor has many editing tools to generate high-quality bone segments and models, including the ability to have overlapping segments. New CT volumes can be generated from specific bone segments using the split volume tool, providing a means to share bone CT data that excludes soft tissue data. Segmented volumes can also be shared or made available to contribute to artificial intelligence-assisted annotation of bone models. By sharing segmentations as well as 3D models, anthropologists will have the opportunity to evaluate CT rendering workflows to determine optimal settings for anthropological applications. In 3D Slicer, data can be collected from volume renderings of CT or microCT volumes or 3D models by placing landmarks or collecting distances and angles, using the Slicer Morph extension to perform morphometrics, or by applying many of the other extensions for collecting quantitative data. MeshLab also has ruler and landmark collection tools, as well as tools for quantifying and visually displaying topological features such as curvature of surface models, collection of geometric data, and surface-to-surface comparisons. Many packages in R, such as Geomorph, support geometric morphometrics of 3D models. Open resources for virtual osteology can be sustained only if generated resources continue to be shared. Web repositories have made it easier to share 3D models as well as CT volumes, and many web packages that support 3D interaction require little coding experience to implement. Export options from 3D Slicer support common file formats that can be easily shared and displayed online, such as 3D models in PLY, OBJ, and STL formats, and multi-model scenes in GLTF format. Many free or open source web-based tools allow sharing of and interaction with 3D models as well as 3D volumes in the browser without the need for users to download and learn 3D software. Some of these include Threejs, 3D Hop, Sketchfab, GitHub, and MorphoSource. 3D HTML pages, such as those generated with 3D Hop or Threejs, can also be attached to R Shiny applications, providing an opportunity to build 3D references to accompany quantitative analysis tools. Many of the web-based tools can be implemented locally rather than online, providing an option for more secure or protected usage by allowing users to download data and web code, or for forensic demonstration purposes. I've provided a link to interactive examples and accompanying data and code for several web tools that may be useful to virtual osteology. Web-based tools can be used to share not just observations or measurements, but interactive examples of skeletal variation, pathology, trauma, metric and non-metric traits, and data collection methods. They can provide reference databases for research and teaching, and a way to share 3D printable models that can be used to generate or supplement physical skeletal collections or forensic demonstration examples. While the sharing of 3D osteological models has many applications, the generation and sharing of bone segmentations as well, generated in 3D Slicer, can support the development of artificial intelligence segmentation models to facilitate automatic segmentations and further increase the objectivity of virtual osteology data. Methods for generating virtual osteological models vary among practitioners and among software packages, and can be expected to vary for different anthropological applications. Evaluation and standardization of methods can only happen with sharing of 3D models and segmentations. Thank you very much for watching and listening, and feel free to contact me with any questions, comments, or for collaborations.